In our next question, I want to talk about what we can do if it happens to be the case that the queries that we've written, the very large, very complex queries we've written, perhaps because those queries are from these normalized data stores, what if they're slow? And what can we do about it? I want to share with you what we do with explain, analyze, and what indices are all about. This question is titled, how do I tell when my queries are fast or slow, and what simple things can I do about them? And we'll talk about the explain, analyze, and indices. Let's take a look. Here, I have a table, and this table has 100 rows, and in those 100 rows, I have some entities, I have some categories, and I have some values. And I'm just going to do a simple query where I figure out what the average value is per category. And for 100 rows, is that going to be fast? Is that going to be slow? And if this is normalized, is that going to be expensive or not? Well, if I want to figure out if it's going to be expensive or not, I might use this explain keyword. And this explain keyword tells me what the query engine thinks it's going to do in order to perform this query. And so if we look at it, what it's going to do is it's going to do a sequential scan on the data. It's going to go through every row of the data. It has some startup cost and some overall cost associated with it. This is how many rows it believes it's going to load. And it's going to take that and perform a grouping on the category. And then it's going to do some sort of aggregation. How does it do the aggregation? Well, for the category, it's going to use a hash table in order to do the aggregation. This is the startup cost and the total cost number of rows that it believes it's going to process in order to do that. And there we go. If I use explain analyze or explain analyze buffers, I also get the actual information for what this table was, or what this query was going to do. And so I probably wouldn't use explain analyze or explain buffers willy-nilly for inserts and updates and deletes, because it's going to actually go and perform that operation. But for select statements, of course, what's the harm of doing a select like this? And you can see it has now annotated this with some additional information. What the actual time was, because the query engine can only kind of guess, the actual number of rows it looked at in both of these cases, and with the buffers, the actual memory usage, and how much time it took to set up the query plan and how much time it took to execute the query plan. If you look at this, you'll see that the planning time was more expensive than the execution time. Setting up the query took more time than actually performing the query. Well, that makes a lot of sense. There's not a lot of data. It's probably all resident in memory. It's going to be a pretty fast query, but this may be the case for something like a stored procedure or a prepared statement might be an advantage, because if I'm doing this query over and over and over, I don't really want to pay this planning time over and over. Maybe I can find a way to pay that planning time up front. But beyond that, it's going to be a little tricky for me to do anything to make this that much faster. Because let me show you what happens if I increase this to 100,000 rows. Then I start getting something that's a little bit slower. And you can see it gives me its estimated time, and you can see what it's going to do. It's a very similar query that I was doing before. It's going to do a sequential scan. It's going to do a group. It's going to do an aggregate. And then I've added one more step. I'm doing a sort. Note that the sort, adds some time to this overall process. And one question might be, what else could I do to speed this up? Well, maybe I could use an index. When we think about pandas, we think about the index as being a very different thing. And sometimes people say the index is like a primary key, but not really, because primary keys are unique, whereas a pandas index doesn't have to be unique. The index is really the mechanism that we use to describe how an operation is performed. It is the intermediary that describes what happens when you express an operation. It's expressed in terms of index alignment. Whereas in SQL, the index is more of a mechanism that prevents you from doing unnecessary disk reads. This sequential scan is a big spot where you might want to perform some optimization. Because what you can think is, this query plan tells me it has to go through every single row of data. It has to scan through all of these. And if this is a very large amount of data, that could be a lot of disk reads on maybe slow storage. And even if not on slow storage, it's still a lot of disk reads. It's still a lot of memory accesses. Sorry, a lot of disk accesses, which we know tend to be slow. However, if I had an index, the index could be an intermediary that says, if you're trying to find this particular value, this is where you go and you find it. And it could shortcut me so that I don't have to do it as many discretes. And you could think this is where the analogy for the pandas index is, because the pandas index is a mechanism that translates between some human labeling and a physical position. It translates between the lock and the iLock via the get_lock. However, if I add an index here, I would anticipate seeing no real speedup on this query. Let's take a look. 29 milliseconds without an index. I'll add an index on the category, and it's 29 milliseconds with the index. And you can see that even with the index, it's still doing a sequential scan on the data. Why? Fundamentally, your query engine is going to try and figure out what the most efficient way to perform this query is. Sometimes it'll get it wrong, and that can always be frustrating because you have to coerce it to do the right thing, and you're limited in your ability to just tell it, please take this approach. However, if you look at the query is going to select each category and the average of every value, grouping these categories and sorting by category. That sort is going to be very fast because you're only going to sort 3 rows for category A, B, and C. The hashing is going to be, moderately okay. And you can see here the amount of time here is quite extensive to actually do the aggregation itself. But what you can see is the sequential scan on the data is also taking 8 seconds. Well, it has to do the sequential scan because the query is saying operate on every row. So why would it go through the index to try and cut down on the number of rows that it wants to operate on if by virtue of how I constructed this query, it has to look at every row? Where I would see a benefit with that indexing is if I were only looking at a subset of rows. Give me the aggregate if I only want category B, or if I only want categories that are not B, categories A and category C. Well, you can see if it's not category B, we didn't really speed up. But if we look at just category B, we can see we get a significant speed up here from 28 milliseconds to 12 milliseconds. Why? Because it's able to use that index to identify, hold on a second, don't load this, and don't load this. Just load the pieces that I care about. So I've loaded less data in total. I've done fewer disk reads in total. And each one of the steps above is going to speed up a little bit, but really not by that much, because you can imagine that, if this data is evenly distributed, then, if I do it with this categorization versus everything but B or everything, you're talking about twice as much data or 3 times as much data. You wouldn't expect you actually might expect something pretty large because you are processing less data. But you get the general idea that the whole point of the indexing is to really reduce the total number of disk reads you have to do by taking these predicates and pushing them down as far into the query to minimize disk reads. And you can see that quite clearly on the explain, because you can see a very simple query with a sequential scan that takes 19 seconds versus a query with a bitmap index scan that takes 1 second. And it's 1 second to figure out what rows you want to load, and then 5 seconds to actually do the data analysis, and then some sort of grouping and aggregation, and then the ordering as well. Indices are not the solution to every problem. When you do the explain analyze, there's a lot of information to look at and to visualize. Generally, your solutions are going to be figuring out how to make the query look at less data up front. And you'll see that via the query plan. The query plan will tell you, I'm loading a lot of data here. But you can also see it from the query itself. The second thing is, when you're performing some sort of filtering, making sure that the filtering that you're performing can be done efficiently. So that's where you might use indices. You might say, well, this is a very big table with millions of rows. Don't read through every row to identify if it's a row that I want. Make sure the index has that. The third thing that you might do is you might understand, and you'll be able to see it from the query plan, where you are either doing very expensive queries. For example, you have subqueries and you're doing lots of queries in a loop, or where you have optimization barriers. And I've said before that things like common table expressions historically have represented optimization barriers. You can't optimize past them. And maybe that's the case where when you look at the time, you say, well, hold on a second. I don't need to do this entire query because later on I do a filtering. I can either push that filter into the original query, or I can have SQL figure out how to do that by not having the optimization variable, by doing this as a subquery as opposed to as a common table expression. And you'll be able to see all of these from the query plan. In general, the query plan will give you a lot of information. It's almost always the case you want to do like the analyze with the buffers to see, how many disk reads it did and to see how many rows it did. But for the most part, what you're really looking for are cases where it's loading way more rows than it needs to load, or where for some reason there's a very large amount of time and it's because it's doing a scan that could be sped up, or where it just doesn't need to spend that time because it could be looking at less data from the beginning. And so that's a very brief introduction to those tools. There's way more that you can ascertain, and there's more options for explain and explain analyze. But I'd really encourage you, whenever you have a very large query, to at least benchmark that query, to look through how the query would be executed, and to try and start getting an intuitive sense for how the query works.